Welcome to Lecture 5. Today we are examining the implementation of Intrusion Prevention Systems, or IPS. Traditional network security relies on the standard firewall. These devices operate using static rules, deciding whether to allow or deny traffic based on a rigid checklist of IP addresses and ports. Modern cyber threats are engineered to evade those perimeter defenses. Attackers use dynamic payloads and obfuscation techniques that a simple static checklist cannot detect. Defending an enterprise network requires a solution that moves beyond predefined static rules. The system must analyze the actual behavior and context of the traffic as it flows in real time. Relying solely on passive, rules-based defense mechanisms leaves an organization's internal assets exposed the moment the outer perimeter is breached. Closing this security gap requires an evolution in network architecture, the Intrusion Prevention System. An IPS inspects the actual data payload within the network traffic to identify and actively block malicious activity. This process relies on automated real-time interception. The system analyzes the data stream and executes mitigation commands before the traffic finishes crossing the network boundary. This active interception is distinct from older security models, such as standalone detection systems, which merely log malicious events after the intrusion has already occurred. Deploying an IPS reconfigures the network perimeter as an intelligent, active checkpoint rather than a passive observation wall. To understand how these systems execute their commands, we have to look at the architectural differences between detection and prevention. A standard intrusion detection system operates in promiscuous mode, often referred to as monitoring mode. This split-path network diagram illustrates promiscuous mode. The IDS sits off to the side, receiving a copy of the traffic. The original malicious packet still reaches its target server, while the IDS only generates an alert. Prevention requires a different architecture. An IPS mandates an inline mode deployment, placing the hardware directly on the single line of communication. Because all traffic is forced to pass through the device, the IPS can physically intercept and drop malicious packets before they reach the endpoint. Placing a security device directly in the traffic path does introduce operational risk. If the IPS appliance hardware fails, it breaks the physical connection, disrupting all legitimate network traffic. Ultimately, the deployment mode dictates the security capability. A system cannot prevent an attack if it does not directly control the traffic flow. This enterprise network topology diagram shows that an organization requires different types of IPS deployments depending on the specific node being protected. The primary layer of active defense is the network-based IPS, or NIPS. The NIPS is placed in line at network choke points, typically right behind the main firewall, to monitor the broad flow of all incoming data streams. Further downstream, individual assets require a host-based IPS, or HIPS. Installed as software directly onto individual devices or servers, a HIPS provides highly granular protection tailored to the specific operating system running on that machine. To secure radio frequencies, administrators deploy a wireless IPS, or WIPS. Attached to the wireless network, the WIPS monitors the local spectrum to specifically detect and block rogue access points attempting to bridge into the system. Effective intrusion prevention relies on this distributed, layered architecture, ensuring active interception at every potential ingress point. Regardless of physical placement, the IPS relies on specialized internal logic to identify a threat within the packet stream. The most accurate method for stopping known attacks is signature-based detection. In this diagram, we see the IPS opening a data packet to examine its code. The system compares this data against a database of known signatures, predefined patterns that act as a digital fingerprint for specific malicious payloads. The most direct matches are triggered by atomic signatures. An atomic signature analyzes a single standalone event. If one individual packet matches the database, the defensive action is triggered instantly. More complex attack patterns require composite signatures. A composite signature requires the IPS to analyze a sequence of multiple packets over time. It groups these seemingly harmless packets together, identifies the hidden pattern, and rejects the combined sequence. Signature detection guarantees high accuracy against known threats, but its efficacy is entirely reliant on matching against a pre-existing database. The millisecond a signature match is confirmed, the IPS executes an automated action. Depending on the configured policies, the appliance will drop the malicious packets, block the offending IP address, reset the TCP connection, and generate an alert for the security team. However, this strict reliance on existing signatures creates the system's core limitation: the inability to detect zero-day attacks. A zero-day attack exploits a newly discovered vulnerability. Because it has no predefined pattern in the threat database, the IPS scans the payload, finds no match, and views the attack as legitimate traffic. Because the system cannot recognize unknown patterns, continuously updating the IPS signatures is the most critical maintenance task for network survival. We can observe how these components interact by analyzing 3 real-world mitigation scenarios. In the first scenario, a known malware variant attempts to enter the network. The NIPS reads the payload, matches an atomic signature, and successfully drops the packet at the perimeter. For threats that lack a specific signature, such as volumetric attacks, organizations deploy Network Behavior Analysis, or NBA. This line graph illustrates an NBA system during our second scenario. It establishes a traffic baseline, detects the exponential volumetric spike of a DDoS attack, and actively blocks the malicious sources to flatten the curve. In the third scenario, a compromised internal account attempts unauthorized lateral movement. The HIPS on the target server detects the unusual behavior and terminates the session, preventing an insider threat. By implementing a multi-layered IPS architecture, organizations can effectively address external malware, volumetric flooding, and internal breaches simultaneously. Successfully implementing this architecture begins with defining strict security policies and selecting the exact IPS types that match the network's bandwidth and topography. During configuration, administrators must carefully tune the detection rules. Poorly tuned rules generate false positives that block legitimate work, or false negatives that let attacks slip through. A distributed architecture also requires integrating the IPS hardware with a Security Information and Event Management System, or SIEM. The SIEM aggregates the data, allowing security teams to manage and correlate alerts from the NIPS, HIPS, and WIPS in a single centralized dashboard. Once deployed, administrators must maintain a rigorous automated schedule of signature updates to keep the threat intelligence current. An active inline IPS, when carefully configured, continuously updated, and properly monitored, is an essential component of modern layered network defense.